Cloud computing and data infrastructure. Cloud computing and data infrastructure have become integral components of today's digital landscape, fundamentally transforming how organizations manage, store, and analyze vast amounts of data while accessing critical computing resources on demand. Traditionally, companies maintained their own data centers, replete with physical servers, storage devices, and networking equipment, all of which required substantial capital investment and continuous maintenance. However, the advent of cloud computing has redefined this relationship by offering a scalable, customizable, and cost-effective alternative that leverages remote data centers, virtualization technologies, and advanced networking to deliver resources over the Internet. At its core, cloud computing is the practice of using remote servers hosted on the Internet to store, manage, and process data rather than relying on local servers or personal computers. This model provides a flexible, on-demand approach to accessing computing power, enabling organizations to scale operations quickly without the burden of physical infrastructure investments. Rather than purchasing and maintaining their own hardware, businesses can rent virtualized resources, benefiting from economies of scale, streamlined management, and the agility to adapt to changing workload demands. The process of virtualizing computing resources allows multiple virtual machines to run on a single physical server, maximizing hardware utilization and reducing energy costs, while also enabling a variety of applications to coexist in isolated environments. Complementing cloud computing is the concept of data infrastructure, which comprises the underlying hardware, software, and networking technologies that support the storage, processing, and transmission of data. Modern data infrastructure is built upon distributed computing architectures that span multiple geographic locations, ensuring high availability, redundancy, and speed. By utilizing a network of interconnected data centers, organizations can replicate and back up critical data, significantly reducing the risk of data loss due to hardware failures or unforeseen disasters. This distributed model supports not only the storage needs of cloud computing but also the advanced analytical tasks demanded by contemporary data-driven applications. A critical enabler of both cloud computing and data infrastructure is virtualization, which revolutionized the way computing resources are allocated and used. Virtualization allows a single physical machine to be divided into several virtual machines, each running its own operating system and applications. This separation enhances resource utilization, as workloads can be balanced across virtual instances dynamically, thereby reducing idle time and optimizing performance. Building on virtualization, containerization takes a step further by packaging applications and their dependencies together in isolated environments known as containers. Containers are lightweight and can be deployed rapidly across different computing environments, ensuring consistent performance and simplifying the process of moving applications between development, testing, and production phases. Orchestration platforms, such as Kubernetes, help manage these containers, automating deployment, scaling, and operation, and further bolstering the resilience and responsiveness of modern data infrastructure. The global expansion of cloud service providers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, highlights the move towards centralized management of data resources through distributed data centers. These providers have invested significantly in building networks of secure, high-performance data centers around the world, allowing businesses to deploy applications closer to their end users and minimize latency. This global presence supports diverse regulatory and data sovereignty requirements while delivering robust, consistent performance regardless of geographical location. By leveraging these services, organizations can harness powerful computing resources without the encumbrances associated with setting up and managing their own data centers, thereby accelerating innovation and reducing time to market for new applications and services. In addition to providing the raw power of computation and storage, cloud platforms offer an array of managed services that enhance data infrastructure capabilities. These services include scalable databases, serverless computing, data analytics, machine learning platforms, and Internet of Things, IoT, frameworks, which collectively allow businesses to process and analyze large datasets in real time. Data lakes and data warehouses, for instance, provide specialized repositories where vast amounts of structured and unstructured data can be stored and queried. Machine learning and artificial intelligence services then draw upon these data resources to generate insights, automate decisions, and even predict future trends with a high degree of accuracy. The seamless integration of these offerings within the cloud ecosystem has accelerated the digital transformation journey for enterprises across various sectors. Security is a paramount concern in the realm of cloud computing and data infrastructure, especially as data becomes increasingly centralized and accessible via the Internet. Enterprises must adopt robust security measures to protect sensitive information stored in the cloud, employing techniques such as data encryption, multi-factor authentication, and role-based access control. Cloud providers continuously update and enhance their security frameworks to meet evolving threats, often employing artificial intelligence to monitor and respond to potential breaches in real time. Furthermore, compliance with international data protection regulations requires that cloud infrastructures implement strict security protocols to safeguard not only the data but also the privacy of the users involved. The ability to maintain rigorous security standards is one of the key drivers behind the widespread adoption of cloud services by corporations and governments alike. Another emerging aspect of modern data infrastructure is the integration of edge computing, which shifts certain processing tasks from centralized data centers to the network's periphery. As more devices become connected through the Internet of Things, IoT, the volume of generated data grows exponentially, making it increasingly impractical and inefficient to send all this data back to a central cloud for processing. Instead, edge computing allows data to be processed locally, thereby reducing latency, decreasing bandwidth usage, and improving real-time responsiveness. This is particularly critical in applications such as autonomous vehicles, industrial automation, and smart cities, where immediate processing of data is essential for safety and operational efficiency. Edge computing works in tandem with centralized cloud systems, extending the capabilities of modern data infrastructures and ensuring that critical insights can be derived with minimal delay. Financial flexibility is one of the most compelling advantages of cloud computing and robust data infrastructure. The pay-as-you-go pricing models employed by cloud service providers mean that businesses only pay for the resources they actually use, which drastically reduces the barrier to entry for smaller companies or startups that might otherwise be unable to afford high-performance computing systems. This flexible billing approach not only optimizes operational expenditures but also facilitates experimentation and innovation by allowing companies to rapidly scale up or down as needed. The cost efficiency inherent in cloud computing empowers organizations to focus on their core business operations while delegating the complexities of infrastructure management to specialized providers. Cloud computing and data infrastructure also play a transformative role in enabling distributed and remote work environments. By providing secure access to data and applications over the Internet, cloud technologies have made it possible for teams to collaborate effectively regardless of their physical location. Virtual desktops, cloud-based file sharing, and collaborative platforms enable seamless communication and project management across geographically dispersed teams. This shift toward a more flexible work culture has become even more pronounced in recent years, as organizations worldwide have recognized the strategic advantages of remote work, such as increased employee satisfaction, reduced overhead costs, and a broader talent pool. The resulting digital workspace not only bolsters productivity but also contributes to a more resilient business model in the face of unexpected disruptions. The evolution of cloud computing and data infrastructure continues to be driven by ongoing advancements in technology and the growing needs of data-intensive applications. Emerging trends such as quantum computing promise to further revolutionize the capabilities of cloud platforms, offering unprecedented speeds and processing power that will enable even more complex data analytics and simulation tasks. As these technologies mature, they will likely be integrated with existing cloud systems, creating hybrid models that leverage both classical and quantum processing to solve problems that are currently intractable. Additionally, the adoption of artificial intelligence and machine learning in managing and optimizing data infrastructure is poised to further automate operational tasks, reduce maintenance costs, and enhance the overall performance of cloud environments. Organizations that embrace cloud computing and invest in a robust, scalable, and secure data infrastructure are well positioned to drive innovation and maintain a competitive edge in today's rapidly evolving digital economy. By transitioning to cloud-based services, businesses benefit from faster deployment of applications, improved data analytics, and the agility to respond to market changes in real time. The move to the cloud is not simply a technological upgrade, but a comprehensive transformation that affects every aspect of an organization's operations, from the way customer data is handled to the efficiency of internal processes. As a result, companies that leverage the full potential of cloud computing are able to streamline workflows, foster collaboration, and ultimately deliver superior services to their customers. In essence, cloud computing and data infrastructure together form the foundation of modern technological progress, powering the digital transformation initiatives that are reshaping industries around the globe. These systems offer the scalability, agility, and security necessary to support the ever-increasing demands of big data, artificial intelligence, and emergent technologies such as IoT and edge computing. With the pace of innovation showing no signs of slowing, organizations must continue to invest in and adapt their data infrastructures to stay ahead of the competitive curve. Ultimately, the strategic integration of cloud computing not only drives operational efficiencies and cost savings, but also opens up new opportunities for growth, innovation, and value creation in an interconnected world. As we look to the future, the advancements in cloud technologies and data infrastructures will undoubtedly continue to unlock new possibilities and redefine the boundaries of what is achievable. The shift towards remote work, the need for real-time insights, and the push for digital transformation across all sectors underscore the importance of these technologies. Their ongoing evolution represents a critical enabler for economic development and societal progress, setting the stage for a future where digital data and computing resources fuel the next wave of global innovation. Embracing these technologies today will empower businesses and governments to tackle the challenges of tomorrow, ensuring a more efficient, connected, and resilient world where the power of the cloud drives transformative change.